Subscribe to my channel and press the bell icon for latest notification about my videos.
Welcome to all of you today to our channel. It's Sributi and our topic of today is electric potential energy. So let's start. For the topic of electric potential energy, let us consider two charges as we considered in our previously class 10 knowledge of electricity. With there, we have learned something about electric potential. What was that? The term of electric potential was referring to us as something that the work done in bringing a uniform positive test charge from infinity to a point within an electric field is termed as electric potential, and the energy associated with that potential is termed as electric potential energy. But by continuing with that same reference point in our class 12 syllabus, we'll be getting something a big calculation, but it's easy too. Let's check what's that. Consider two charges, suppose it to be Q1 and Q2. Let us fix this charge Q1 at a point supposedly to be A, and this point and them as B, and if this fixed charge Q1 is kept at A and this B point Q2 which was present previously and the point where this charge Q2 is present, let it be unfixed. So if we take the charge Q2 from B to another point, suppose that point to be somewhere here to be C, then what will be the result? Suppose the distance of the charge Q1 to Q2 be R, and the distance between A to B is R1, and the distance between B to C, supposing this to be R2. So we are getting the total distance between A to C as R1 plus R2 and the distance between the two charges Q1 and Q2 as R. So from here we know that the basic force which these two charges will be having between them, that will be something according to the Coulomb's law as like of F vector is equals to Q1 Q2 by 4 pi epsilon naught, or 1 by 4 pi epsilon naught, which termed as K, or force constant, Coulomb's constant. So, and this is the K into Q1 Q2 into 1 by R square, or we write here R square. So this is the force which is applied on between these charges Q1 and Q2. Now if we check the work done in making or in shifting the charge of Q2 from B to C, then it will be somewhat a big task. So let us consider a very small displacement of Q2. Suppose over here, that is, let me write it with blue as dr. Let a small displacement over here from Q2 as dr. Okay. So we will be getting another term associated with it. The work done over here, that work done will be is equals to integration of F vector dot dr. This is the very fundamental top formula for the numerical value of work done by any object, any body. So if we apply the same property over here, what we will be getting? We are getting the force over here, and the displacement we know that is dr. So let us substitute the value of F over here as W equals to integration of F, that is Q1 Q2 by 4 pi epsilon naught into R square, and this is dr dot dr. Now the body was shifted from a distance r1 to a distance r2 completely, as in a single throw it was done displaced to a distance dr, and for completing or for the total displacement of the body was from this B to C, that is R, total distance R2, just from that position R1 which was B to the position R2 to the position C. So the limit over here in the integration will be R1 to R2. Now if we solve this, what we will be getting? Let's see. This will be Q1 Q2 by 4 pi epsilon naught will be a constant and come out of the integration. It will be somewhere like Q1 Q2 by 4 pi epsilon naught outside the integration, here R1 to R2, and this dr and r square will combine. If we do the integration of separately of dr, of integration of dr will be r, and integration of this r by 1 by r means it will be dr means r by r square means 1 by r, or if you remove the integration sign you will be getting a box value of something like this from R1 to R2. So this case is incomplete. Let us complete this case. Come over here, it will be Q1 Q2 by 4 pi epsilon naught, and this is, first we will be putting the value of R1 as 1 by R1 minus the value of R2, that is 1 by R2, which is equals to the work done by the body to shift its position from Q2 B to C. There is a charge to shift the charge Q2. The net work done in shifting the charge from B to C is Q1 Q2 by 4 pi epsilon naught into 1 by R1 by minus 1 by R2. This is the value of here. But if we check that as the point Q at A, as the charge Q1 at A is fixed, so it will be having an electric field over here, and as it is fixed, so the work done will be only associated with the charge of Q2. So if we get the net work done, this final minus initial, we'll be getting as something like this, as U at R1 minus U at R2 is equals to the work done according to the work energy theorem. As if we assume that the body is totally displaced without any loss of kinetic energy, and the entire potential energy is used, so the work done equals to the potential energy, which is according to the work energy theorem. So final minus initial will be getting as minus W, as previously it was less and after that it is negative, it is more less, so final minus initial term is negative over here. So if we do this as this term as W, if we make it negative, then we will be getting as Q1 Q2, or if we write or minus W is equals to Q1 Q2 by 4 pi epsilon naught into 1 by R2 minus 1 by R1. This is the net work done by the charge Q2 when the charge Q1 is fixed at A. This condition only satisfies the electric potential energy of this point. So we are getting that electric potential energy of the body W, of the body Q2 with the reference to the body Q1 at A is equals to Q1 Q2 by 4 pi epsilon naught into 1 by R2 minus 1 by R1. Now this is a special case over here when the body A is fixed, but if there are multiple bodies, suppose the bodies there are 3 charges, 4 charges, 5 charges, or n number of charges, at that case we simply adding their electric fields according to the vector addition rules. So for that purpose, if we consider that the initial body was at infinity, okay, the initial position, as we got the definition of electric potential, that the energy or the work done in bringing a unit test positive charge from infinity to a point within electric field is termed electric potential, and the energy associated with it is electric potential energy. So if we consider the initial position of the body to be infinity and the final position of the body to be r, then we'll be getting as the result as net work done W is equals to Q1 Q2 by 4 pi epsilon naught into 1 by r minus 1 by infinity, and this is 0, so it will be only 1 by r, or if we shift over here it will be somewhat looking like this. Means W is equals to Q1 Q2 by 4 pi epsilon naught into r. This is the work done by a single body. Now if there are multiple bodies, 2, 3, 4, 5 to n bodies, then we will be simply adding this single entities with the number of times, but in accordance with the vector addition rules. This point is to be kept in mind, as this all are vector quantities, and work done though is a scalar, but force is a vector quantity. So for adding up the forces, we have to do the vector addition rules, and for doing the work, we'll be obviously adding it with scalar rules. So that point is to be kept in mind. So it's all about our videos of today. All the best and study hard.